now we're going to talk about bond polarity. And I'm going to grab myself a pen here. And bond polarity, it investigates deeper in those three types of bonds, or those two types of bonds that we've been talking about. Mainly the ionic bond, which is right here, and the covalent bonds, which are right here. And we'll start with the ionic bond first. In the ionic bond, we have the total transfer of electrons from the metal, which is right here, to the nonmetal. So you can see how right here the nonmetal, which is the anion, has gained the electrons, and it shows both of the dots over here, and this guy over here is totally naked. He has no electrons of his own, so that's why he's positively charged. So that is a very big difference between the electronegativities of A and B, and we categorize that as an electronegativity difference of greater than 1.7. That was our E and D, if you recall from our last lesson on ionic bonds. So there was a line here that I drew, and there was a 0, and there was a 1.7, and there was a 4.0, and if the electronegativity difference was way up here, then we classified it as an ionic bond, because there was a complete transfer of electrons from the metal to the nonmetal. Well, these guys over here, they are sharing electrons. And sometimes when two friends get together, they share very nicely, and those electrons end up right smack dab in the middle. And sometimes when two friends get together, one friend decides that he wants a bigger share of those electrons. When one atom has an electronegativity that is greater than the others, he pulls those electrons just slightly closer to him, and because of that, he becomes slightly negative. Now remember, electrons are negatively charged, so if the electrons are slightly closer to the guy who has the higher electronegativity, that side of the molecule, and we can call them molecules because they're covalently bonded. If you recall, covalently bonded substances are called molecules, and ionic are called salts. So we can call these molecules where there's an uneven sharing polar covalent, and if there's an even sharing, we call that non-polar covalent. Let's take a look at an actual example of things that might be non-polar covalent and other things that might be polar covalent. Alright, let's say we were talking about diatomic hydrogen. And in diatomic hydrogen, there is only one bond. We've drawn this as a Lewis dot diagram, and we've also drawn it with the line right there, which indicates one single covalent bond. So we're actually talking about this bond right here. Now, hydrogen has an electronegativity, En, of 2.2. This hydrogen has an En of 2.2. So when they get together and they're fighting over these two electrons, I can actually draw them as electrons for you. Da-da-da-da. So let's draw them. I'll make them red. When they're fighting over those two electrons, this hydrogen right here that my cursor's on is pulling with a strength of 2.2. And this guy who is also pulling on those electrons with a strength of 2.2. So those electrons that are right there underneath my cursor are going to be right smack dab in the middle. That is a non-polar covalent bond. And the way that you can remember that it's non-polar is that the word non is symmetric. Symmetric. And that bond right there between those two hydrogens is symmetric. And if you don't know what symmetric means that if I were to take a line, and I'll make it this funny green color, if I were to take a line and I were to divide them into two, I'm going to take a vertical line right now and divide it. The left side and the right side would be identical. And the top and the bottom would also be identical. So it's symmetric both left and right and top and bottom. And if you have a bond that is symmetric both top and bottom and left and right, you can now say that you have a non-polar covalent bond. Now if we take a look at this bond between hydrogen and chlorine, you can see that hydrogen would have an electronegativity of 2.2, whereas chlorine would have an electronegativity of 3.2. So let me get my pen back out here, 3.2. And if you don't know where I'm getting these numbers from, I pulled up Table S for you to look at. Table S is in your reference tables, and Table S has the electronegativities, which tells us how strong an element is. So I got the hydrogen's number from right there, and I got the electronegativity of chlorine from right there. So when these two atoms come in contact with each other, this guy is pulling with a strength of 2.2, and this guy is pulling with a strength of 3.2, and they are fighting over these electrons that are right here in the middle. So chlorine obviously is going to get a bigger share because he is stronger than hydrogen. So in reality, what happens is the electrons are slightly closer to the chlorine, and electrons are negatively charged. So that means that the chlorine gets a slight negative charge, and the hydrogen gets a slight positive charge. So it has basically a north pole and a south pole, or a positive pole and a negative pole. When the electrons are not shared equally, when they are unequally shared between two atoms, you have what we call a polar covalent bond. Now, at the Regents level, the polar covalent bonds will occur when the two atoms are different. Hydrogen is different from chlorine. And notice in the word polar that there are all different letters. There's no letters that are the same. Because they're not the same, that's how I remember that if the atoms are not the same, it is polar. Whereas in the word nonpolar, we had two ends and it was symmetric. Polar covalent bonds are asymmetric. Let's put a cloud around that because it's very hard to see. You might think it's asymmetric polar covalent bond. The asymmetric refers to the fact that the two atoms are not the same. If I were to draw a line down the middle, let's change the color. Let's make it red. If I were to make a line down the middle, I'd have a hydrogen on this side and a chlorine on this side. So it's not the same left and right. So if it's not the same and it's asymmetric, you have a polar covalent bond. And if you have two that are the same, and on the Regents level, all your diatomics are going to be your non-polar covalent bonds, then you have a non-polar covalent bond. Alright, just to recap, I wrote down the basics that you have to absolutely know. If you have a polar covalent bond, remember a bond is only between two atoms. It is going to be asymmetric, and it's going to be between two different atoms, such as, oh, I need a pen, okay, such as HF. And the electrons are not going to be shared equally. The electrons are going to be slightly closer to one of the atoms, the one with the higher electronegativity. So this guy has an electronegativity of 4, this guy has an electronegativity of 2.2, so the electrons are slightly closer to the fluorine. Whereas in a non-polar covalent bond, let's see if I can get that to move, nope. The electrons are going to be shared equally with each other, and they're going to be right in the middle. So this fluorine has a 4.0, this fluorine has a 4.0, and the electrons are right smack dab in the middle. So there's no positive or negative here. Here, the fluorine would be slightly negative, and the hydrogen would be slightly positive. Okay, that wraps up today's show. Hope you have a good night.